Quantum security failures rarely come from broken mathematics. They come from broken assumptions. In this video, we examine a class of quantum attacks that mirrors one of the most persistent enterprise vulnerabilities in classical systems: deserialization. Just as enterprise software fails when it blindly reconstructs objects from untrusted input streams, quantum key distribution systems fail when they blindly reconstruct quantum states from untrusted physical sources. We call this class of failure quantum state injection, and it represents a practical, implementation-level attack surface that does not violate the protocol, does not spike error rates, and does not require breaking the underlying cryptography. What follows is a focused, engineering-driven analysis of how trusted quantum assumptions collapse in real systems, why detection fails, and how attackers exploit the boundary between idealized protocols and physical reality. In classical enterprise environments, deserialization vulnerabilities arise when an application blindly trusts an input stream and reconstructs objects without validating their origin or intent. The application assumes that the serialized data represents a benign object graph, but in reality, the attacker controls the entire reconstruction process. By carefully crafting the serialized payload, the attacker injects a gadget chain that executes implicitly during deserialization, long before any application logic or security checks run. The exploit does not rely on malformed input or crashes. It exploits the fact that object reconstruction itself is treated as a trusted operation. This is why deserialization vulnerabilities are so dangerous in large vendor platforms. They collapse the boundary between data and executable behavior. Once untrusted input is allowed to materialize into trusted internal state, the attacker no longer needs memory corruption or exotic primitives. The application executes the attack on its own behalf. This pattern is important to understand because the exact same trust failure appears in quantum systems, where physical inputs are reconstructed into internal quantum state representations under assumptions that attackers can violate without triggering obvious alarms. The security of BB84 and related quantum key distribution protocols rests on a critical assumption that is rarely stated explicitly in deployment discussions: that the quantum source is trusted and that the states reconstructed by the receiver faithfully correspond to the states that were prepared. Alice assumes that each transmitted signal corresponds to a single photon quantum state drawn from the intended ensemble, and Bob assumes that the quantum states arriving at his detectors represent honest physical realizations of those preparations. The security proofs that guarantee detectability of eavesdropping rely on this assumption, because any deviation is expected to manifest as an observable increase in error rates. What is important to recognize is that the protocol never authenticates the physical quantum state itself. It only validates statistical outcomes after measurement. This creates a trust boundary at the source and reconstruction layers, where untrusted physical inputs are implicitly converted into trusted internal quantum representations. As in classical deserialization vulnerabilities, once this boundary is crossed, the protocol logic operates on an assumption that an attacker can violate without immediately triggering detection. In real-world quantum key distribution systems, photon sources do not emit ideal single-photon states on demand. Instead, most deployed systems rely on weak, coherent pulse sources, whose photon number statistics follow a Poisson distribution. This means that while single-photon emissions are common, there's always a non-zero probability of emitting 0 photons or multiple photons in a single pulse. The mean photon number, typically denoted by mu, is chosen to balance loss and throughput, but no choice of mu eliminates multi-photon events entirely. Importantly, these multi-photon emissions are not anomalies or implementation errors. They are a fundamental property of the source physics. As a result, any protocol that assumes strict single-photon behavior is already operating under an approximation. This is the critical opening for state injection-style attacks, because it establishes that the protocol's security assumptions diverge from the physical reality of the transmitted signals, even before an attacker actively intervenes. At this point, the attacker's advantage becomes concrete. The vulnerability does not arise from violating the quantum protocol, but from exploiting the moment where physical quantum signals are converted into trusted internal representations. Alice emits weak coherent pulses, which inevitably include multi-photon states. When those pulses enter the channel, an attacker positioned at the trust boundary can identify and selectively interact with the multi-photon events without disturbing the remaining signal. Crucially, the attacker does not need to alter basis choices, inject noise, or interfere with the measurement process itself. The manipulated physical state is forwarded onward in a form that remains fully consistent with Bob's expectations. When Bob receives the signal, he reconstructs what he believes to be a legitimate quantum state and proceeds with measurement under the assumption that the physical input was honest. This is the exact failure mode seen in classical deserialization vulnerabilities. Untrusted input is transformed into trusted internal state before validation occurs. From the protocol's perspective, nothing anomalous has happened. Error rates remain within expected bounds, loss characteristics look normal, and reconciliation proceeds as designed. Yet the attacker has already crossed the trust boundary and gained leverage over the system's internal state. This is where quantum security proofs quietly stop applying, because the guarantees assume that reconstruction begins from honest physical states. Once that assumption is violated, the protocol continues to function correctly while operating on attacker-influenced input, and detection mechanisms that rely on disturbance or error amplification never fire. This is the exploitation phase of a photon number-splitting attack, and it is fundamentally passive. When a multi-photon pulse leaves the source, the attacker does not interfere with the protocol or attempt to guess measurement bases. Instead, the attacker first identifies pulses that contain more than one photon, which is possible because multi-photon emissions are an unavoidable consequence of weak coherent sources. For those pulses, the attacker deterministically removes a single photon and stores it in quantum memory, while forwarding the remaining photon or photons onward to the receiver without loss or disturbance. From Bob's perspective, the received signal is entirely legitimate. The pulse arrives on time. The polarization or phase encoding is intact, and the measurement statistics match expectations. No errors are introduced, and no protocol rules are violated. The attacker has effectively cloned the quantum information without measuring it, not by breaking the no-cloning theorem, but by exploiting the fact that the system itself generated multiple physical copies. At this stage, the attacker does not extract any information. The stored photon is left untouched. The critical point is that information has been duplicated at the physical layer before any classical post-processing or basis reconciliation occurs. This is why photon number splitting attacks evade detection mechanisms that rely on disturbance, error rates, or anomaly detection. The protocol continues to function correctly, while the attacker silently accumulates perfectly valid quantum states for later measurement. At this stage, the system has already been compromised, yet every metric Bob relies on for security verification remains well within expected bounds. The quantum bit error rate does not spike, because no measurement disturbance has been introduced. Detection rates look normal because photons continue arriving on schedule and within loss tolerances. Timing jitter stays flat, because the attacker forwards legitimate quantum signals without delay. From the protocol's perspective, nothing abnormal has occurred. This is the core blind spot exploited by quantum state injection attacks. All monitored invariants remain satisfied while the underlying security assumption has already been violated. Security proofs for protocols like BB84 are conditioned on the premise that the quantum states entering the receiver were honestly generated and have not been duplicated. Once an attacker copies physical quantum information upstream, before basis reconciliation or measurement, those proofs no longer apply, even though the protocol continues executing correctly. Bob's validation logic is not broken. It is simply checking the wrong properties. The system verifies consistency, not provenance. As a result, the protocol proceeds through sifting, error correction, and privacy amplification under the false belief that the quantum channel was secure. This is why passive state injection attacks evade detection entirely. They exploit the gap between what the protocol can measure and what it implicitly trusts. The failure is not noisy, dramatic, or detectable. It is silent, structural, and complete. At this point in the attack, nothing further happens on the quantum channel, and that is exactly why the exploitation succeeds. The attacker does not rush to measure the captured quantum state, nor do they attempt to guess Bob's basis or interfere with the protocol's execution. Instead, the attacker simply waits. After quantum transmission is complete, the protocol transitions into its classical phase, where Alice and Bob publicly announce their measurement bases, perform sifting, and carry out error correction. This classical disclosure is assumed to be harmless because the quantum measurements are believed to have already occurred. However, the attacker's stored quantum state has not been measured at all. Once the basis information is revealed, the attacker can deterministically choose the correct measurement basis and extract the encoded bit with certainty. No disturbance is introduced, no guessing is required, and no statistical anomaly appears in the protocol's observed metrics. The security failure is therefore not probabilistic, noisy, or detectable through error rates. It is purely temporal. The attacker exploits the fact that the protocol reveals critical information after assuming the quantum phase is complete, while the attacker has effectively delayed that phase by storing physical quantum information. This is where the attack pays off. Security collapses not because the protocol was implemented incorrectly, but because it trusted that quantum information could not persist beyond the moment it was supposed to be measured. Privacy amplification is often treated as the final safety net in quantum key distribution, but it fundamentally cannot repair the damage caused by quantum state injection. Privacy amplification is designed to reduce an adversary's partial information about a raw key by compressing it into a shorter secret, assuming that the adversary's knowledge is limited, noisy, or probabilistic. In a photon number splitting or state injection scenario, that assumption is already false. By the time Alice and Bob reach the privacy amplification step, the attacker has measured stored quantum states in the correct basis and recovered the raw key bits with certainty. From Eve's perspective, there is no uncertainty left to eliminate. Privacy amplification does not remove information that an adversary already possesses. It only reduces information that is incomplete. When the attacker's knowledge of the raw key is exact, the privacy amplification function becomes fully predictable. The compressed key is just a deterministic function of values the attacker already knows. This is why the failure is irreversible once state injection has occurred. The protocol continues to execute correctly, error rates remain normal, and the final key appears statistically secure. Yet secrecy has already been lost at the physical layer. This is not a failure of cryptographic strength or hash function design. It is a failure of the security model's assumptions about when and how quantum information can be trusted. What we are looking at here is not a flaw in a single protocol, but a recurring architectural pattern that appears across both classical and quantum systems. In the classical world, we've seen this failure many times. Untrusted input is accepted, reconstructed into a trusted internal object, and only later checked for correctness or consistency. Deserialization bugs, unsafe parsing routines, and credential handling failures all follow this same structure. The system assumes that reconstruction itself is safe and that validation can occur afterward. Quantum state injection follows the exact same pattern, but at the physical layer. An untrusted quantum signal crosses a trust boundary and is reconstructed into a trusted quantum state before its provenance is verified. Once reconstruction has occurred, all downstream security mechanisms operate on the assumption that the state is legitimate. Detection logic checks consistency, not origin. Cryptographic proofs assume honest state preparation. Privacy amplification assumes partial information. In both classical and quantum systems, the critical mistake is identical. Trust is granted before validation. This is why quantum state injection is not an exotic edge case or a protocol-specific weakness. It is the quantum analog of a well-known system security failure. As long as reconstruction precedes verification, the system can be made to function correctly while being fundamentally insecure. This is not a problem that can be patched with better thresholds or stronger cryptography. It is a failure of where trust is placed in the architecture. The key thing to understand here is that nothing we've shown contradicts the formal security proofs of quantum key distribution. Those proofs are mathematically correct within the domain they define. The problem is that they are conditional proofs, not absolute guarantees. Every security proof begins with assumptions about how quantum states are generated, how they propagate through the channel, and when measurement occurs. In the proof world, state preparation is honest. Single photon emissions are assumed or statistically bounded, and no quantum information persists beyond the measurement event. In the physical world, those assumptions can be violated without breaking the protocol itself. Quantum state injection exploits this gap. The protocol executes correctly, the math remains valid, and all verification checks pass, yet the system is insecure because the proof never applied to the system that was actually built. This is not an implementation bug, and it is not a failure of cryptographic strength. It is a mismatch between an abstract model and a physical reality. Once untrusted quantum input is reconstructed into a trusted internal state, every downstream guarantee inherits that mistake. The lesson is subtle but critical. Security proofs do not protect systems from violations of their own assumptions. They only describe what happens if those assumptions hold. What this forces defenders to confront is that quantum security cannot be layered on top of classical assumptions without rethinking where trust begins. In systems vulnerable to quantum state injection, the failure occurs before cryptography, before error correction, and before any statistical validation can take place. Trust boundaries must therefore move earlier, all the way to the physical channel itself, rather than being inferred from downstream correctness. It is no longer sufficient to verify that quantum states behave as expected. Defenders must validate where those states came from and whether they were formed under trusted conditions. Detection logic must evolve away from purely statistical anomalies and begin accounting for untrusted state injection, even when protocol execution appears flawless. This requires treating the quantum classical boundary as an explicit security surface, not an implementation detail. Physical layer assumptions matter because they silently underpin every proof, every threshold, and every guarantee the system relies on. When those assumptions are violated, security collapses without warning. The takeaway is simple but uncomfortable. Secrecy cannot be restored after a compromised state is reconstructed. If security does not extend to the level of state formation itself, then no amount of cryptographic strength or post-processing can compensate for that loss of trust. This video has shown that quantum state injection is not an exotic corner case or a protocol-specific flaw, but a fundamental failure mode that emerges when trust is placed in reconstructed states rather than verified origins. We saw that the attack is passive, undetectable by statistical means, and invisible to error rate monitoring. We saw that delaying measurement collapses the security model without breaking the protocol, and that privacy amplification cannot repair information that has already leaked at the physical layer. Most importantly, we saw that none of this contradicts the mathematics of quantum security proofs, because those proofs are conditional on assumptions that real systems do not always satisfy. The lesson here is broader than any single protocol or attack. Security fails when reconstruction precedes validation, when provenance is inferred rather than enforced, and when physical assumptions are treated as implementation details instead of security boundaries. Quantum systems do not fail loudly when these assumptions are violated. They fail quietly, while continuing to produce outputs that look perfectly correct. As quantum technologies move from laboratory demonstrations into deployed infrastructure, these architectural lessons matter more than any individual algorithm or cryptographic primitive. If defenders do not explicitly model and defend the physical layer where quantum information is formed and transmitted, then the strongest cryptography in the world will be protecting the wrong thing. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.